Okay, so we looked at some convergence concept called pointwise convergence, right? So we have a sequence of functions, f and x, right? So this sequence actually depends on x, okay? So x defined over some sets, okay, belonging to the set of real numbers, okay? And we look at the pointwise convergence, which is we look at this quantity, right? Okay, it equals to some constant, and this quantity here may actually depend on certain x. So x may be in some interval, okay, and equals to some other number in other intervals, okay. So pointwise convergence has this problem that in the limit, the function that you have, yeah, may not be actually the same thing. Okay, it may converge to different things, right? Depending on what is your x. Okay, this creates a lot of problem if you use pointwise convergence, right, as a convergence criteria. It creates a problem in the sense that the resulting limiting function, right, will actually one of the things is that it won't be continuous. It won't be continuous, so it's not guaranteed to be continuous. It may actually break, right? Once it breaks, then you have problems with differentiation, right? You can't differentiate a function that at the point where it is discontinuous. Okay, so this leads people to develop a new, a different idea of convergence called uniform convergence. Okay, so we have uniform convergence. To start with the definition, yeah, what does it mean? So we look at the definition. All right, definition 3.6.2, uniform convergence of sequence of functions, right? So suppose you have E as a non-empty subset of R, okay? It's not empty. Okay, then if you have a sequence of functions, Fn E to R, SIT to converge is SIT to converge uniformly, okay, on E, if and only if for every epsilon greater than 0, there is an n, okay, in the set of natural numbers, such that when your index n exceeds or equal to this threshold, then the distance between the function, right, the sequence of function, the function from its limit, right, this is the limit of f and x, is bounded by epsilon, right? So the distance cannot, it will be bounded by epsilon, okay, for all x in E, okay? So as you can see, you have studied the convergence concept for the sequence of real numbers, right? So it's basically the same thing, which is this is your main object of interest, right? So this is a sequence of functions. So this is a general notation for the, this is a notation for the general term, yeah, in the sequence of functions. So this is the limit to which you this term converges to. So you bound it, right? So this is basically looking at the distance, right? The distance between this object with its limit. It's bounded by epsilon, right? So the idea is the same with when you deal with the convergence of sequences, okay? And you have to show that this is true for all x, okay? Right? The main difference between uniform convergence and pointwise convergence is that in pointwise convergence, your limit, so this bound here, in pointwise convergence, it needs to depend on x. But in this case, you cannot depend on x, all right? I will give you maybe first a few sketches. Okay, give you some examples where you actually have uniform convergence. Okay, so right, suppose you have some curve like this. Okay, so this is n equals to 1. Right. So maybe I'll just write f1x is like that. Okay, and then you have f2x. Maybe it's like this, and so on, right? Until in the limit, you may actually have something like this. Okay, so this one is your f, right? Which is the limit as, okay. And this is defined over some interval of, maybe let's say this is a to b, right? So it's always with respect to some particular interval, okay? So a function may be uniformly convergent over a certain interval, right? But not over the entire real number line, okay? So, for example, in this case here, right, you see the following. Over here, if you have some epsilon, okay, I'll use blue color, okay, you have some epsilon, right? So what happens is that your deviation, right, from the red line, okay, so it's saying that it won't actually exceed, okay? So you have this. So for the around the red line, okay, you have a deviation from the red line. Let's say maybe this is too small. I'm not very happy with this. Let me clear this. Let's clear it. Right. Okay, much better. So I might have like something like this. I have 1x. Okay. Let me just draw the. This is the let's say this is the curve. This is my f. Okay. Okay, so for some epsilon, right, for some particular epsilon, so if you have f n x subtract f, right, bounded by some epsilon, okay, so it basically means that you are you have something like this. So you have around the limit, it has a deviation of epsilon. Okay. So this is a deviation of epsilon. All right. This is minus epsilon from there. That's plus epsilon, right? So there's actually a band around the F, right? If you have F1, right? Now your F1 here is actually exceeding. It's actually gone out of the bound at certain points, right? Like for example, at this point, it's gone out of the bounds. This point is gone out of the bounds. This point is it's gone out of the bounds. Okay. So your F1 doesn't actually satisfy that. Okay. But let's say you have some. So you keep on having your Fs. So there will be some F such that if you can find some particular F, right? Let's say up to F45, starting from F45 and onwards, okay? If the deviation, right, of these functions from the limit, okay, does not exceed that bound, then you show uniform convergence, right? So for example, if your F45 is something like this, okay? So you can see that the deviation, right? These are so you can see that it deviates from the red line, okay? These are the deviations, right? You can see that the deviation does not exceed the blue line, okay? The blue bounds. So starting from 45 and onwards, you have found it, okay? You have found the tail sequence for which the difference here is true. Then you show that uniform convergence actually occurs. Okay. And there are some sequences that are actually not uniformly convergent. Okay. This one I give you an example of uniform convergence. Let me show you an example where you don't have uniform convergence. Before that, maybe I just check with you. Are you okay with this diagram?
Yes, doctor.
Anyone else has any feedback? Okay with this diagram on uniform convergence?
Yes, doctor.
Okay, let me show you now one example where there is no uniform convergence. Okay, suppose you have some curve that's like this. Okay, this is your F1 x. F2x, so this one is going towards infinity, yeah, as it tends towards 0, okay? So you have F2 is also declining like this, but F1, that's F2. And so on and so forth, right? Let's say you have YF like 100, it's like this. Okay? It's tending towards, as you go towards infinity, is of course dropping towards 0, okay? So in this case, this function, right, is actually, it has a pointwise convergence. So this F1x is something like maybe some form like this, okay? So if you take, sorry, this is n. So if you take limit, right, definitely this occurs, right? You take limit of these is equal to, as your n becomes very large, so this will be, so let's say I define this over until, sorry, this is your x. Maybe I just define until 1, yeah, okay? So your x is between 0 and 1, right? If you take n tends to infinity, so that means you are looking at this sequence of curves, right? They will, so you take limit over n, so this will be tending to 0, but only for so for x, okay, right. So it will be equal to 0. That's actually a pointwise convergence over x in this interval. Okay. However, I claim that there's no uniform convergence. Now, the reason is here. You keep on having this, right? So the line to which it converges to, right, supposed to be 0, okay? Because this is the limit, yeah? So it's actually this red line, okay? The 0 line here, okay? This line, right? So you have a band here, okay? So you have the epsilon. So you have an epsilon, right? So the deviation from the limit. So it'll be something like this. So there's a, oops, there's a band. There's a band like this. Wait. Okay. Okay, at the same distance, right? So of course, you can say that if you look at F1, definitely it's out, right? If you look at F1, its deviation from the red line is out of the blue band, okay? The same with F2, right? It's out of the blue band, right? Now, for this F100, it is okay until this point, right? Until this point, it's within the blue band, but outside of that, it's outside of the blue band, okay? So 100 also doesn't work. So if you keep on doing this, right, if you keep on having higher and higher ends, I claim that you will never find it, because the point is, when you look at this function, right, when your x gets arbitrarily close to 0, your f and x will shoot up very quickly, okay? So there is always some x, right? There is always some x here, a little bit of it here, right? Such that your f and x will go outside of the band. Okay, you can't find that. No matter how hard you try, yeah, you can push your x to be very, very close to 0. It doesn't matter. There will still be some small interval here, such that the moment you have some very small x, it will shoot up here. And it cannot be completely enclosed by this band. All right. So this is an example of a sequence of functions that does not converge uniformly to 0. Okay. Although it does converge pointwise. Yeah. Okay. So this one gives you a graphical feel to what convergence of sequence of functions is. Okay. Once you understand it graphically, then the analytic work is usually much easier to handle. Okay. So let me clear this. So if you look at the example 3.6.3, I asked that we show this to be converges uniformly to 0, all right, for x in R. Okay. All right. So basically, you need to show that this guy here, since it converges to 0, so this is your f and x. This is your fx. We need to show that this is bounded by epsilon for for n greater than or equals to this n, right? Okay. So how do we show this? So in this case, it's very easy to show analytically because 1 over n of, so the left-hand side here is basically just equal to this. You can take off the absolute symbol here because this guy is always positive, right? And this is subtraction of 0. So basically your left-hand side is equal to this guy. And this guy is basically less than or equals to 1 over n, right? Because this guy here is more than 1, right? It's always more than 1, isn't it? So when you have something more than 1 multiplied by n, so it will be always, if you compare it with this guy, so this will always be, the right-hand side will always be larger than the left-hand side, okay? So is it clear to everyone why this is true? This guy is always less than, more than or equals to 1, right?
Yes.
Okay, so you are dividing by a larger denominator. So of course, it will be smaller, right? If you just multiply it with 1, right? So this is bounded by 1 over n, and here is very simple already. You just bound it with the large n, okay? And you bound it with epsilon, and therefore you choose n greater than 1 over epsilon. That will do. The point is that you have to find some epsilon, so find the threshold n that depends on the epsilon. This cannot depend on x. One of the usual problems that students come into when they try to show uniform convergence is that they are not able to get the right-hand side here that is free of x. You have to find some suitable bound that will eliminate x on the right-hand side. If you cannot find it, it's not uniform convergence because your bound depends on the x. Okay, so for uniform convergence, you have to find suitable bounds for this particular distance. Okay, and then I give you another example. Clear this? Okay. This.
Doctor.
Right.
Sorry to interrupt. There's a student waiting to be admitted into the meeting. If you would like to admit her, thank you.
Okay. Oh, okay.
Thank you, Doctor.
Just let me know, right? Sometimes because once I start talking, I may not be very aware of the people in the waiting room. Okay, just let me know. Okay. So you have this sequence. This sequence is just a shorthand. Like when I write a sequence of functions, right? By right, I should write it like this. But since every time I'm writing this guy here, so I'll just omit it, right? Okay, for simplicity. Okay, by write a sequence of functions, you have to denote it like you are starting from some particular index. Okay, but generally, when I suppress this, it means that there's actually this thing there. Okay. So, okay, show that it converges uniformly to 0 for x in the set of real numbers, okay? So again, for this case, we need to show that there is, so this guy here is bounded by epsilon. When n exceeds this threshold, right? And this threshold will depend on epsilon, okay? So the first observation here is that now sine function can be positive or negative, right? So the first thing is that I note that my absolute of sine x is bounded by 1, right? Okay, your sine cannot go out of 1 and cannot go out of -1, right? So when you take absolute, this simply means that your sin x is bounded by 1 and -1, right? Okay. So this is the first observation. So once you have this, then you know that your left-hand side is equal to sin x over n, right? Absolute of n has no effect because n is positive. And directly, this is bounded by 1 over n, yeah? Because the numerator is bounded by 1, yeah? So very easy. And therefore, this is bounded by 1 over big N and bounded by epsilon. So again, this one is n greater than 1 over epsilon, okay? So this is also relatively simple. And the graphical illustration for this convergence, uniform convergence, is given in figure 3.6.2. Maybe I share that with you. Okay, can you see the figure? Can you see figure this, the figure of sin nx?
Yeah.
Okay. So as you can see, so your 0 here is the limit of sin nx over n, yeah? As your n tends to infinity. So the red line is the bound, right? The plus minus epsilon boundary away from the limit. So you can look at the first curve here, right? First curve here is your sin nx over n for n equals to 1. And then you have the dotted line is n equals to, so this dotted line here is n equals to 2. So you can see that at certain points, right, it actually goes out of the red band, okay? So it doesn't satisfy. So you haven't found a big N yet, okay? And you see that as you go along, so this dotted line here is 10, yeah? That's when your N is equal to 10. And it's actually touching the red line, right, at certain points, okay? It's touching the red line, okay? So it's not yet, right? Because you want the distance to be less than epsilon, all right? So at n equals to 10 is touching. So starting from n equals to 11 and onwards, then it's no longer touching, yeah? Okay, so over here you can see that by the theory, right, we show that our big N must be larger than 1 over epsilon. So here the epsilon I chose 0.1 is equal to 10. So N has to be some threshold that's larger than 10. So I will choose N equals to 11, yeah? So starting from, that means when your small n is 11 or more, it's definitely the deviation, right, from the limit will not get out of the boundaries, okay? So I didn't show n equals to 11, but I showed n equals to 20, right? You can see the blue curve there, right? So the blue curve, you can see that the deviations are here, right? So you just try to imagine, oops, don't want that. Okay. So you can try to imagine the deviation, right? From the blue line going to the black line, right? It's definitely bounded by the red lines. Okay. Right. So the point of uniform convergence is that you can find some threshold, right, such that when your index, the small n exceeds, is equal to this threshold or more, the tail sequence of your function, they will all have the property that they cannot escape from the limit by more than a certain amount that's determined by epsilon. So in this case, it doesn't matter if you choose to shrink your epsilon. Suppose you shrink your epsilon. If you shrink your epsilon, the red line simply goes down, right? Okay, you can shrink your epsilon in such a way that n equals to 20 is no longer valid, right? Because the blue will go out of the red band. It doesn't matter because you can find some other n some other big N, such that the function here will be will be contained by the red bands. Okay. The point is, you can always find such a big N. Okay. If you can find it, then you show uniform convergence. Okay. All right. So one more example. So this is example 3.6.5. Okay. This is to show uniform convergence of this sequence. X over x squared over n squared. Okay. X positive or x non-negative. Okay. So the claim is Fn x converges to Fx uniformly. So this is 0. Okay. So basically, you want to show this, right? That means trying to show that this is true when your small n is greater than or equals to this big N. Okay. Now, how do we show this in this case? All right. Some of you might actually try something like this. So the left-hand side equal to this. You can take off the absolute sign because your x is positive. Yeah, your x is not negative. Some may actually want to try something like this. Okay, but since the denominator has some added term, but this doesn't work because you see you can't get rid of this x, right? To show uniform convergence, you have to sort of like go up to some point where, so you can't do something like this, right? Because then this inequality here will contain x, and to show uniform convergence, x cannot be involved, right? It cannot depend on x. So this doesn't really work. Okay, so we need to use a different kind of idea. Okay, so this is to show to you different ways of approaching a proof, right, for uniform convergence. Okay. Now, how do we show this? So the first idea is to show that f and x is bounded by sup. Okay, so this function here is bounded by the sup. To see why, okay, so suppose your fn, right, is some function like this. Okay, so up to this point, it's some function like this. Okay, so what is your, so this supposes a f and x, right? So your absolute of f and x will be like this. So this part flips up, right? Okay. Over here, then it. Okay. So this is your absolute, right? So this is your x, yeah. So when you say sup of that, that means you find the supremum, right? The supremum of this function. Okay. The supremum here is basically just a more general way of finding the least upper, the smallest upper bound, right? So there are many upper bounds, isn't it? This is an upper bound. This is an upper bound, right? There are many upper bounds. Okay, here is an upper bound. This is also an upper bound, right? The sup is the smallest upper bound. Okay, so where's the smallest upper bound here? In this case is somewhere here, right? This is a soup, right? Okay. So definitely, so the soup of absolute f and x is this line here. And definitely, if this blue line bounds your absolute of f and x, it will definitely bound this guy, okay? So it will definitely bound your f and x. So it will be here. Okay? The point is this soup, the soup of absolute f and x is sometimes easier to find than the soup of f and x, okay? But the point is that your f and x will definitely be bounded by the soup of absolute, okay, over some interval of x. All right. So how do we find this? Okay. Now over here, you first need to find if there's a so if there's some kind of supremum, right, over here in the interval, right? As long as it's not at the edges, yeah. If it's in the interval of your the interval for which your x is defined, you can use differential calculus to find it. Okay. So you can find you want to find this point. Right. So you want to find, because you want to find this line, right? So this line is equal to this particular point here, right? It's maximized at this particular point, right? So at this particular point, is stationary. Your function is stationary. Okay, the derivative, the gradient is flat, right? So that's why you can find d dx f and x, and you set it to 0. Okay, that will give you the stationary point over here. All right. So to illustrate, so for this case here, your f and s, your f and x. Maybe let me erase this. So your f and x is you differentiate, right? So basically differentiating this guy here. So it will be x squared over n squared times 1 minus x times the derivative of the denominator with respect to x, so 2x. Okay. Then x squared plus n squared squared. Okay. So basic calculus. So this will give you n squared minus x squared over x squared plus n squared squared. Okay, set to 0. This can only be 0 when your x is equal to n, right? Okay, the denominator doesn't affect the 0 here, only the numerator. So only when your x is equal to n, right? So because of this, okay, since my f and x is bounded by soup of this, okay, this whole thing here, the soup of this guy is equal to, because you found the maximum occurring at n, right? So you basically, this whole thing here is just n over n squared plus n squared. Okay? So you see, to approach this problem, right, you have to have several dimensions of understanding the problem. You cannot just rely on some tricks or moving things around, like algebraic tricks. It doesn't work in this kind of analysis. Okay, you have to first understand what it means by the supremum of a function. Have some sketches of that so that you understand the concept, and then you can connect all these operations. So the supremum of the absolute of this thing here occurs, it basically is just we want to find this blue line here, right? So this blue line you can find by differentiating. Okay, you can find by differentiation. After that, you know that it occurs, the max of the supremum occurs at x equals to n. So this is 1 over 2n. Okay. After you cancel off the n, right? So once you have this, so definitely since your fnx, right? Since your fnx is bounded by the supremum, so basically this is, in this case, this is your fnx, right? It's bounded by the supremum. Okay. Then basically it's done already, because over here, once you find that it's bounded by 1 over 2 small n, then you can change it to the big N and bound it by epsilon, right? Therefore, you find that your epsilon has to be greater than 1 over 2 epsilon. Sorry, your N. Okay. So the trick here is to actually notice this relationship. Yeah, this relationship is important. That your f and x is bounded by the supremum of the absolute of f and x. Okay, and the supremum here, you have to think of it as the, yeah, okay, connected to this part here. Okay. Okay. So I think we will stop the today's lecture at this point. Okay. I don't want to go to the. So the next part here, the next part is to actually tell you some interesting properties of the uniform convergence. It turns out that if you have this uniform convergence, then it allows you to interchange the operation of limit and integration. But that will take more than 10 minutes to talk about. So I'll leave that for next week, right? So we just stop at showing uniform convergence, right, of sequences of functions for today. Okay. And then we will get ready for the presentation for tutorial 1 by the students. Before that, we handle some logistics first. Yeah. So I have already issued tutorial 2. If you look at tutorial 2, it's in the spectrum. Yeah. Okay. So there are 7 problems in tutorial 2. Okay, and so we will just do 5 questions because problem 6 and 7 are related to the interchange of limit and integral. Okay, so that one we leave it for later. Yeah. So I got 5 questions there. Maybe you can take a look at the first 5 questions, and we have some students to maybe try out these questions.
Doctor, I have a question.
All right.
I have a question.
Yeah.
Why is our f(x) always 0?
Sorry?
Why our f(x) is always 0?
Why is the fx?
Yeah, always 0. Because the 3 cases we took, all of them are 0.
I don't understand your problem. Wait, what is the question actually?
My question is that f(x) minus f(x), right?
You're talking about 3.6.5?
Yeah.
Uh-huh.
Why our fx is like all of them are zero, like three of them are zero here, and then the previous two are zero.
Maybe let me.
Sir, he's talking about the examples, all three. We saw there's f of x equal 0. So he's saying that are there other...
Yeah, of course.
Okay.
Of course, there are. It's not always going to 0. It's just that for these examples, the limit is it uniformly converges to 0. Actually, 0 itself is a function, isn't it? It's a constant function.
Yeah.
In fact, there are some, because you see over here, right? This function here, it can actually you can actually have convergence to this, something like this, you know. The point is that it converges to some function. All right. In fact, like a constant is also a function, right? It's just a flat line, right? Over all possible x. Like over here, you have one flat line. This is still a function, right? It's just the function is just a constant over this interval, right? But it could also be some functions. Okay. Doesn't matter. It will actually depend on what is your sequence of functions.
Okay.
Later, you will actually come across some. In fact, I think in the lecture notes, there's an example of sequence of functions that converges to exponential function. You look at, I think if you look at figure 3.6.1, you can see that, okay, maybe I show it here. Okay, this figure. Oops. Can you see the figure?
Yes.
Okay. This is an example where the sequence of functions converges to something that is not a constant function. For example, you look at the function is 1 minus x over n power n. So you can try out different values of n, or n equals to 1, n equals to 2, n equals to 3, 4. So and so on and so forth, right? Then I show until 10, so you get some curve that's going down like this. I'm sure if you remember your calculus, right? If you keep on taking your n to be very large, 1 minus x over n raised to the power n, in the limit will converge to exponential minus x, right? If you look at this curve, right, already n equals to 10, the approximation is very good already. Okay, it's already looking more or less like exponential minus x. So this is an example where your functions, right, it actually converges to something that is like a non-constant function. Okay.
Okay. Thank you, doctor.
But it's actually to show uniform convergence to some function that is not a constant function. It's actually not so easy if you play with inequalities. That's why the examples are given, right? They are all like constant functions. And of course, among the constant functions, the simplest one is 0, right? Because when it's 0, when you take the absolute sign, it's easy to manipulate, right? That's why the illustrations are usually given with example where the convergence is to the constant function of 0 rather than some other constants.
Okay, thank you, doctor.
Yeah, okay, sure. Okay, if you look at tutorial 2, let me look at tutorial 2 now. Okay, can you see tutorial 2? This is tutorial 2, can you see?
Yes, Doctor.
Doctor.
Okay. Well, anybody wants to pick up these problems? We will just look at 1 until 5, yeah? 6 and 7, not yet. Okay.
I think I want to try problem 2.
Problem 2, so who is next?
Nabiha.
Okay, let me just record it, yeah? Nabiha, okay, no Nabiha. Okay. How about number 1?
Me, Dr. Hidayah.
Oh, okay, Hidayah. This is just showing convergence of sequences using the definition, right? Of you play around with the epsilon thing, so it gives you some practice on some exercise on using that kind of concept. Okay. Problem 3.
I will take it. Since
Oh, Xinji. It's simple. Problem 3 is just giving some examples.
just 1 or 2. I need to give 1 or 2 example.
Give some examples of subsequences that converge and some that do not. You can give one. I mean,
Okay.
like one example where it converges, another.
And 1 for diverge.
Yeah.
Okay, sure. Thank you.
Problem 4 has A, B, C, D, so we can actually split to 2 students. One will do A, B, the other will do C, D. Anybody?
Doctor, I can do Doctor. Problem 4. Parvin.
Parvin, okay.
Yeah.
You do A, B lah.
Yeah, okay, Doctor.
Doctor, I can do CD. I'm cousin.
Albert.
Yeah, Albert.
Okay. How about 5? Actually, 5 is already a giveaway. I kind of like talk about it just now, but using some instead of talking about 1 over nx, I just talk about 1 over nx square. So it's kind of like a giveaway already. But this is just kind of like if you work on this problem, you just have some reinforced learning. Anybody wants to try this?
Doctor, I will try. Karim.
Karim?
Yes.
Sure. Okay, Karim will try this. You can actually check back the video just now to get some ideas. All right. Okay. So that's done. Okay. So we have the presentation now. Let me look at the questions. Tutorial 1. Okay, so maybe I will enable screen sharing by the students. So first question is for tutorial 1 is ohm, right?
Yes.
Okay. Let me see. I have to change the setting a bit. Okay, maybe I have to make you host or something like that.
All right.
Okay. Then you have to make me host again, yeah?
Okay.
You're done, all right. Make host. Yeah, I think you can share your screen now.
All right. Can you see my screen now?
Yeah, sure. I can see your screen.
All right.
Okay,
Okay.
yeah. So you can just talk about it.
Okay, so this is problem 1. Find the infimum and supremum of these sets. So the first set is this, E equal to set of 4, 3, minus 2, 1, 8, 7, minus 6, and 5. So I arranged them like this. And the definition of a supremum is of a set is the least upper bound, and the infimum is the greatest lower bound, I think. Correct me if I'm wrong.
Yeah.
So the least upper bound here, the least upper bound here is 8. So the supremum of E is 8, and the greatest lower bound is minus 6. So the infimum of E is minus 6.
Okay, that's right.
All right. So B, the set is like this: X of is real numbers, all real numbers, and we have this inequality. So we have to solve this inequality because it's a condition in the set. After that, I solved it. X1 is this and X2 is this, and then I tried to plot, not plot it, just visualize it in a way. They said that it should be less than 0. So this is the region where it's less than 0. So we have the set is basically this, and so E is equal to this to this, and then obviously the supremum of E will be the lowest upper bound, and the infimum is the greatest lower bound. Am I correct here?
Yes. Yeah, that's right. Basically, this is just a quadratic equation, right? So basically, if you draw a curve,
Yes.
yeah, of course, you draw a curve, then so basically, it will be something like this, right? I mean, like you didn't show the curve, but that's fine, yeah. It's going downwards, and then it reaches some kind of a minimum, and then it goes up again, right?
Yeah, I could have just drawn the curve of this one and see the intersection with 0, right?
Well, well, if you just sketch the quadratic curve, then it will be clear that you need to find the roots of the quadratic equation so that you will know the interval for which the function is actually negative, right?
Yes.
Yeah. So, but basically, it's just a kind of like slightly different approach that you have done.
Yeah. This is more old school, like high school style.
Yeah. Sure. So,
Alright.
so basically, yeah, that's okay.
So this is the third one. I'm not sure of this one, but I tried it. It's 1 plus minus 1 to the power n over n, where n is like natural numbers, all natural numbers. Natural numbers are from 0, right? Like all.
Oh, it starts from 1.
Oh, okay. So from 1 to infinity, all integers. So I said if n is odd, then this is equal to this one, 1 minus 1 over n. And if n is even, then this function is equal to 1 plus 1 over n. So I tried something like this where since all natural numbers begin from 1, so I replaced the n here with 1, and it's equal to 0. So it's gonna be bounded between 0, like it's equal or greater than 0, and the maximum thing would be 1. And then if n is even, so we start from 2 because 2 is even, 1 is odd and 2 is even. So it's gonna be the least would be
So sorry,
yeah.
This question is it will be much easier if you just list down
Just to see a pattern, like list down the numbers, like n equal to 1 and n equals to 2.
So it's okay, you have done the first part, like if it's odd is 1 minus 1 over n, and it's even is 1 plus 1 over n. Okay. So after that, you start to list down, right? So the first element is odd. So you use 1 minus 1 over 1, right? That will be 0. The second element is even, so you use 1 plus 1 over n. So there will be 1 plus 1 over 2. And the third element will be you use switch back to 1 minus 1 over n. So that's 1 minus 1 over 3. So then you list down that set.
Okay.
From there, to see the infimum and supremum will be easy. You can, yeah, that's why you can't see your supremum there because you didn't list it down.
Yeah.
Yeah. So you can try that. The infimum, sorry, the supremum, if you do it like that, you will find that it's 3 over 2.
Okay. Yeah, it was a bit confusing here. I didn't know how to write the set. I didn't know how to write the set.
Quite easy to write down. Just follow the formula there and write down one by one. So the infimum you will see is 0, okay? But the supremum, well, you need to write down the set so that it's clear, okay?
Okay. All right. Thank you. And the last one is this one. P over Q is all rational numbers, and we have these two conditions. So yeah, I just tried doing this, and yeah, it's just like this is my working. I'm not sure if it's correct, but I'm assuming it's correct.
So it's basically saying that your set E is a set of rational numbers, right? Such that P square over 2Q square, P square is less than 2Q square, and your PQ
and P and Q are
positive, right?
Yeah.
So basically, this is basically taking a subset of the set of real number, rational numbers, isn't it? It's taking a subset.
Okay.
Because it's basically a subset of the set of rational numbers such that your P square has to be less than 2Q square, okay? So which is basically saying that your P of Q has to be less than square root of 2.
Yes.
Right? So basically this involves taking the subset of rational numbers that are between 0 and square root of 2.
Yes.
Right? Because you can, so you can always find some rational number that is very, very close to square root of 2. It doesn't matter. You can put P and Q, you can pick P and Q however large so that they are very close to square root of 2, right?
Yes.
So therefore your supremum is square root of 2 and your infimum is 0.
Yeah.
Yeah, that's correct. Because your rational number can never be square root of 2 because
that's why I put I didn't put less or equal. I just put less. It cannot be part of Q.
Yeah,
like I said here, it's an irrational number, therefore square root is not part of rational numbers.
Right. But then you can actually that can be a supremum. That can be the lowest. Sorry, the
greater the
lowest upper bound.
Upper bound, yes.
Yeah, because your P and Q, in principle, you can make it to be such a large number that they just get arbitrarily close to square root of 2.
Yes. Yeah.
So, okay, that's okay for this.
Thank
Okay,
you.
thank you, Om.
Okay, hold on. Sorry.
Okay, you make me host again, yeah?
Yes. I can't. Oh, it's here. Sorry. I just admitted someone who's been waiting, okay?
Yeah, it's okay. Am I the host now?
You are host now.
Okay.
Thank you.
Okay. So, okay, so I'm going to make somebody else. Okay, so I'm going to, so the next person is Atira, yeah?
Yes, Doctor.
Okay, Atira, let me share Atira. So I make you host, yeah? Okay, you can share your screen.
Do you see my screen?
Yes, yes.
Can see?
Yes, I can.
Okay. So for the problem 2 is about countable set. The first one is explain why the set of triangular number 1, 3, 6, 10, 15, 21, 28, and 36 ... is countable. So this one, the triangular number are given by the following explicit formulas: Pn and k equal to 1, k 1 plus 2 plus 3 plus until n, and the final one is n plus 1 over 2. So I let fx equal to x plus 1 over 2 is bijective, which x is a positive integer. So the first one, when I want to prove like it is countable, I use the bijective. So first, need to show it is one-to-one function. If fx equal to fy, then x equal to y. Suppose fx equal to fy and x and y are positive integer, then x plus 1 over 2 equal to y plus 1 over 2. Then I get x plus 1 over 4 equal to y plus 1 over 4. X plus 1 over 2. This one is factorizing, about factorizing. So I get x plus 1 over 2, y plus over 2, then x equal to y. So the second step is to show it is onto, which is mean each element of y must be paired with at least one element of x. So y equal to fx, then y equal to x plus 1 over 2. So 2y equal to x plus 1, 2y plus 1 over 4, x plus 1 over 2, power of 2, then square root 2y plus 1 over 4 equal to x plus 1 over 2. Square root 2y plus 1 over 4 minus 1 over 2 equal to x. Then x in form of y, so fx equal to f, square root 2y plus 1 over 4 minus 1 over 2 equal to y. Then given any y, f is onto, therefore I conclude set of triangular number 1, 3, 6, 10, 15, 21, 28, 36, and f is countable. So for the second one, the question is show that the set of odd integer 1, 3, 5 is countable, and what can be said about the countability of the set of prime number. So for this one, consider the set of odd integer e equal to 1, 3, 5. Let x element of e, then fe equal to 1, 3, 5.
Akira, can you scroll further down to your solution? I just want to have a look.
This one.
Yeah. Okay.
I'm not
So okay, never mind. Okay. Yeah. Okay. So maybe I give some comments here, right? You don't actually have to show it like this. You just need to show that as long as you see the one-to-one is simply is countable when you have when you can map the natural numbers to the set, right? So that means you have like the number 1 can be mapped to, like, for example, set of triangular numbers. 1 maps to 1, 2 maps to 3, 3 maps to 6, and so on and so forth. So basically you don't have to show all these things. You just need to, if you can construct some kind of formula, right, that represents the general term in the set of triangular numbers, which you already done, which is what is it? N times n plus 1 over 2, right?
This one.
Yeah.
The first one.
Constructed the general term already, n over n plus 1 over 2, right?
And
you already show that it's countable because your n, right, you start from natural numbers 1. So if you have n equals to 1, you have your t1. N equals to 2, you have your t2. Finish already. So yeah, so we don't have to go through all this because I never talk about the things in step 1 and step 2. So yeah, you just keep it simple, yeah. As long as you can express the general term as some kind of a function of n, you are done already. Okay. Yeah, it's supposed to be quite simple. Okay. Number 2.
Same for the question 1.
Show that the set of odd integers is countable. It's the same thing, right? Your odd integers is basically just what? General term is 2n minus 1, right?
Minus 1.
Yeah, 2n minus 1. So basically, when you have n equals to 1, then you have 2n minus 1 equals to 1, and so on and so forth. So therefore, it's countable. Okay. So what can be said about the countability of the set of prime numbers? Well, the set of prime numbers is actually a subset of the set of odd integers, right?
Yes.
Okay. So it's a smaller set. Your set of prime numbers is a smaller set than the set of odd integers, right? So so if the larger set is already countable, the subset of it must be countable. Yeah, you just argue like that, right? Because if you have a larger set, you show that it's countable, then any subset of this larger set is definitely countable.
Yes.
Okay, you just need to argue like that. Yeah, very simple. So in fact, just keep when we explain something, we use the suitable amount of complexity. Yeah. So although the things that you say here, they would be something that people do in a real analysis course. But for this, we I think we will just keep it to the explanation that I used just now. Okay. Thanks. Ira. Yeah. So we have to rush a bit. I just forgot. I should let Hajali present. She's here.
It's okay. It's okay, Doctor. I'm free today for the whole session.
You're free today.
Yep, because it's Friday. Yeah.
Oh, okay. Sorry.
Where should I click to make you host?
Okay, let me see. Actually, I can reclaim host, no problem.
Oh, okay, Doctor. Thank you, Doctor.
Yeah, sure. Then problem 3. Problem 3 is Sutha.
Yes, Doctor.
Sutha here?
Yes, Doctor.
Yeah, Sutha. Okay. So make you host.
Can you all see my screen now?
Yeah.
Okay. So for the first question, this is the graph that I plotted. So for FE, we just have to get the straight image of where this -3 and 1 will plot into. So -3 will, the FE will be 16, and for 1, it's -4 here. So since our -3 and 1 is a open interval, so FE will have an open interval as well. And then for F inverse of E, we portray this interval onto our y-axis and see where it brings us to in the x-axis. So our -3 goes into 4/5 and 1 goes into 0, and it's an open interval as well.
Okay.
Okay, for question 2, similarly, -1 and log surd of ln 2 goes into e to the power of -1 and 0.5. I'm missing the square bracket here actually, I'm sorry. So it will give a closed interval here as well. And then for F inverse of E, this thing, log 2 here and -1 here. -1 doesn't go anywhere since the graph here is only above the x-axis. So the log 2 here goes into this blue dot here and this blue dot here, which I did the calculation, and it's -0.4282 to 0.4282.
Okay, just a minute. So this one is 0. If you put square root of log 2 there, that will be log 2. So so what would this be actually? This is e minus 1. Okay, that's fine. -1 comes in there. Square root of log 2 comes here. Is it 0.5? You will sub in?
Square root of ln 2 is 0.83262.
Oh, we don't have to do that. We just there's no need to do the exact calculation. So you put in square root of log 2, you square it, it becomes log 2, right?
Yeah.
So okay, that's correct. Okay, there's a minus there, so it becomes 1/2. Okay, right. Then the second part, sorry, I missed the inverse just now. The inverse.
The inverse is ln 2 here, goes straight back to x-axis again. And when I did the calculation, I actually calculated it and made it into numbers so that it will be easier for me to move around.
So you have -1. So okay, so yeah, that's right. So you have -1, so it maps to nothing because the curve is until it's positive, right? So then you have the square root of log 2 is here, right? So you will map to, yeah, so you map to these 2 points. That's correct.
Okay, doctor. Question 3, I'm not really sure. So for FE, I assumed that since this is a sine graph, it goes from 0 until infinity. So since the sine always cycles around -1 until 1, so I think the FE will never go outside of -1 and 1. And it's a closed bracket because our 0 here is closed. And anywhere in between infinity, it might be closed as well. Is it
Okay. So this is okay. Your FE is cycling between, so it's cycling between -1 and 1, right? For when your E is going from 0 to infinity. That's correct. So the inverse is basically, let me see.
If I put a 0 to infinity into the y-axis here, I thought that somehow it will go back to 0 in the x-axis, which is why it's a sole number without interval here. I'm not sure if I'm right.
Okay. So okay, so you have, if you put it on the y-axis, right? Okay, maybe this part I will talk about it. All right.
Okay, doctor.
Okay, thank you. Go back to.
Do I need to stop sharing? And
I will reclaim host. Okay.
Okay.
And I will share screen. Okay, let me clear my board. Can you see my board?
Yes, doctor.
Okay. So you have this. You have this function. Okay. Your sine function is like this. Okay, x. So you have 0 to infinity going like this. Okay. So now if you do inverse, right? So basically you'll start from 0, you go all the way to infinity, right? Now when you start from 0, right, you look at the intersection here. So you cut like this, right? You cut like this, right? So it will map to this point, this point, this point, this point, and so on, isn't it? So infinity maps to nothing because so it maps to nothing. So the only points that it gets mapped to will be these parts. Okay.
Oh, okay.
So so that will be, so your F inverse of E will be so this is 0, right? This is 0, so this will be what? Pi, is it? And 2 pi.
Pi.
3 pi, right? So it will be the so okay. So you see, so you see it maps like this. All right. Okay. Because you see your 0, right, is running from, sorry, your E is running from 0 to infinity, right? So it's this line. So it keeps mapping like this, right? So it will map to this, it will keep mapping, it will map to all these values here. So then it will be blank, right? So from pi to 2 pi, there's nothing, okay? And then after that, you keep on mapping to all these intervals. So we want to describe this interval, you see. So this interval here is actually what? The interval from 0 to pi. And your union, the interval from 2 pi to 3 pi. And union interval from 4 pi to 5 pi. And so on. Okay. So basically, you will have what? Basically, this will be union of. So you see this part here is 0, 2 pi, 4 pi, and all that. So it will be 2k pi. This will be one more. So it will be 2k plus 1 pi. With your k going from 1. So going from 0 until infinity. Okay, so your F inverse of E is actually this set. It's a little bit more subtle than the previous examples.
Okay, doctor.
Okay, when you do inverse mapping, you must sketch the plot, yeah. Otherwise, you cannot see it very clearly. Like just now, you were able to do that question on E minus x squared because you sketch it, right? You need to know that you know that this function looks like the bell curve because this is just kind of like your normal density, right? Without your normal density has a constant here. But there's a 2, right? But basically this is more or less similar to your normal. So you know that it's something like a bell curve, right? So that's why when you have your E is from -1 to square root of log 2. So you know if you do the inverse is -1 log 2 is square root of log 2 is here. Because you know that this part is 1, right? So therefore the trick is to, when you do the inverse mapping, you cut here, right? So basically all this will it's from -1 to actually it will cut others, right? So let me see. Would that not actually give you something like this from this interval onwards? I think just now, Suta, you give something that is yeah, maybe not so accurate. I think you gave some interval, right? That is some, I forgot what was that. But the correct one should be if you put the square root of log 2 there. So you have E minus x squared equals to square root of log 2. So you take log, so you have minus x squared equals to log of square root of log 2. Okay. Then your x is plus minus square root of log 2. Okay, so this point here will be log of square root of log 2. And this point here will be minus log of square root of log 2. Okay. So basically, so your F inverse E actually is the set from here, minus infinity until minus log square root of log 2 square root of 2. Sorry, there's a square root here. So inclusive, and then union this set, right? Which is square root of log 2. Okay, until infinity, inclusive. Okay. Okay, so later maybe in the solution you will see it more clearly. Right. Okay, Suta.
Okay, doctor, I think I got the concept wrongly.
Yeah, yeah, just need to sketch a little bit. Sketching is important. If you don't sketch, you can't get the inverse mapping correctly. Okay. All right. Okay. All right. Sure. I think we are a bit off time already. So it's a Friday. So I think I have to. I better stop here now. It's okay. We can talk about the other problems next week during the tutorial together with the other questions. Okay. In fact, maybe yeah, I will just give you the or you can just check the solution later. All right. Okay, so I will stop the recording now.